Okay, let's get started. What do you need to know? This is the equation of the sinusoidal wave, in terms of pressure. A is for amplitude. F stands for the frequency. And T is the time. Wait, hold up. Let's go back, shall we? A sound wave is a wave of compression and rarefaction, by which sound is propagated in an elastic medium such as air. When you play an instrument or listen to your favorite song, you are listening to sound waves. They transcend through frequencies. If we want to get technical, I must add sound waves are produced when the vibration disturbs the particles in the surrounding medium, and those particles disturb the next and so on. The wave carries the sound energy through the medium, usually in all directions, and less intensely as it moves farther. I must add, sinusoidal waves are not easy to calculate, like at all. I'm joking, ha ha ha. Well, sort of. Sinusoidal waves can be easy to calculate, if you have all the factors that contribute to the research of such mathematical curve in music, especially in glimpses of songs.
I would like to see it.
Okay, so you will need to know the wavelengths, the wave period, the amplitude, the frequency, what note you are analyzing, and of course their relationship all together. Wow, that is a lot. Yikes. Okay, now let's go back to present time. This equation should be familiar to you, especially sin. Sin starts at 0, remember? Now that I have refreshed your memory, let's move forward to some examples. This is note A. Now this is how note A looks like as a sine curve. The note produces a wave shaped represented by sin of 2 pi times 440x. Recall, the 2 pi is the circumference of a circle, and at sine, the circle starts at 0. As for the period of the function, the wave has 440 complete cycles every second. This is the time, since there is a certain number of cycles that are completed each second. Multiply it all together, and it equals 880 pi x. Let us throw it back to Unit 7. We could find the area under the curve from the first wave cycle. We would have to find the 0 from the start to the end of the cycle by first graphing sine of 880 pi x. Changing the window from 0 to 0.01 would be preferable. Then we would analyze the graph to find the first 0. Calculate the integral of sine with the limits 0 to 0.001136. Now let's talk about the contributing factors. First, a wave period. A wave period is the measure of time it takes for the wave cycle to complete. It is usually measured in seconds, and represented by the letter T. The wavelength is the distance between one of its peaks and the next peak. Wavelength is represented by the Greek letter lambda, which looks like this. Ugly, right? An upside down Y. Anyways, you may notice that the distance between peaks is the same as the distance between troughs. We can also measure wavelength from one trough to the next. Either way, the wavelength will measure the distance of one wave cycle, or one completion of the waves repeating up and down. Frequency is the number of periods or regularly occurring events of any given kind in a unit of time. One completion of a repeating pattern is called a cycle, hence Hertz, the unit for frequency, which is expressed in cycles per second. It's usually depicted as F. Amplitude is a measurement of vertical distance of a wave from the average line. Take into consideration that bigger waves have larger wave heights, or in this case, amplitude. And remember, velocity is the derivative of position. How do they all relate? Frequency equals velocity over wavelength. Wave period is the reciprocal of frequency, or wave period is wavelength over velocity. Now let's analyze a snippet of a song. By the way, little disclaimer, what was calculated in these videos represent a minuscule portion of the guitar solo. The amplitude of the curve of these various notes is 1. Since it represents the peak, the max would be 1 and the min would be -1. Nevertheless, the frequency was determined by the hertz of the musical notes. Basically, the frequency is given when it comes to music. The speeded clips are the other notes that compose the second of the amazing guitar solo. Listening to sounds such as music and noise has a significant effect on our moods and emotions because of brain dopamine regulation, a neurotransmitter strongly involved in emotional behavior and mood regulation. As a disclaimer, we are not Einsteins. We had a week to process all of this, even to understand the basics of physics in relation to calculus. So please don't judge us, all you bands geeks and physics nerds. Lol. Thank you.